Alright, so we're going to say a couple things about Maclaurin series. So these are really simple kind of Taylor series. It's basically an infinitely long polynomial and, okay, so for a lot of functions there's a way to write down what the infinitely long polynomial corresponding to the function is, and that's what we're going to do in this problem. So just for concreteness, look at this first expression here. F of x is equal to natural log of 1 plus x. Okay, so what we want to do is find the right-hand side of this equation. It's going to be like an infinitely long polynomial that agrees with natural log of 1 plus x on certain values. Okay, so this, we're using the fancy sigma summation, but it's just a sum of numbers times variable, right? Some number c0 plus some number c1 times x plus some number c2 times x squared, and it just goes on like that forever. So that's a power series, and it has a free variable x, right? So you know that for power series they're kind of sensitive about when they converge to actually add up to some kind of finite amount. So the x values they can actually put into the infinitely long polynomial and get a value out for are called the values in the interval of convergence. So on the interval of convergence we are going to, well, we're going to write down an infinitely long polynomial expansion of natural log of 1 plus x, and on the interval of convergence of the right hand side they are going to be the same function. And what that means is when you put a valid value in here and do these arithmetical operations, you know, plus, times, powers, you get a number out, and that number, say you put 1/2 in here, will be the same number that you get when you put 1/2 into this expression, or whatever it is that's on the left hand side. So we've talked about a rule for making the infinitely long polynomial. So notice that the x's, you know, the x's just do what the x's do. This is x to the 0, this is x to the 1, x to the 2. What you really need to know in order to write down the polynomial corresponding to the function is just what these c's are. Right? These, you could call them coefficients of the polynomial. And there is a formula which is very easy to derive. But for Maclaurin series, this is the formula that gives you the nth coefficient. Alright, so this 0th one, for instance, is going to be f of 0 over 0 factorial. So, you know, funnily, ironically, the lower values are kind of maybe more confusing. What's the 0th derivative of a function? We just define that to be the function itself. So plug 0 into the function itself, and what's 0 factorial? 0 factorial is defined to be 1. So really what this is just f of 0. Alright? So if we were going to begin, I don't want to start the problem this way, but if we were going to start writing down the power series for natural log of 1 plus x, then the first thing we would do is we would just write what happens when you plug in 0 is 0. So we're off to a great start. So the infinite sum begins 0 plus blah 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 blah. Okay, so it'll make our lives easier. I mean, we're only going to be able to write down finitely many terms, right? So the real trick is to kind of figure out what this is for a generic index, or a generic n. And to do that we have to figure out kind of how to talk about the generic derivative of the function. This is the nth derivative of the function. So you know only certain functions have like kind of a, I don't know, these nice functions that we're going to be dealing with, there's some regularity in their derivatives that make this thing kind of easy to figure out. So let's just get started here. So we're going to try to figure out a rule for what the nth derivative of the function is. So the 0th derivative of the function is just itself, which is natural log 1 plus x. Okay, now what happens when we take one derivative? Well, the derivative of natural log is 1 over well, yeah, you could say that it's 1 over the input when the derivative of the input is 0. If you use the chain rule, it's more complicated. Alright. So notice that you can think of this as 1 plus x to the minus 1 if you want to. And yeah, okay, so what happens when we take the derivative? Again. So this is number 2. What we're going to do is kind of guess the rule for making a typical one. So the negative 1 comes down, and you get 1 plus x to the minus 2, right? And we can do it again. So what happens if you do it again? Now negative 2 comes down, right? And you get positive 2 out here. So maybe I'll just write it as 2 times 1. Is that going to be confusing? Okay, I won't do that. And now we've got 1 plus x times, or to the power negative 3. And let me just do it, I think, one more time. You'll see what's going on if you haven't already guessed. So take the 4th derivative. Now you get this negative 3 coming down, and it's negative 3 times 2 times 1 plus x to the minus 4th. And if you have any kind of experience with these things, then you can see that what's happening here is that we're building up a factorial in front, and that the signs are alternating. So the signs are alternating, we're building up a factorial in front. So what is the nth derivative going to be? Well, you just kind of write down what rule is being followed here. It says if n is 4, you've got 3 factorial up front, right? So, and when n is 3, you've got 2 factorial up front, and that works for these other cases too. So in the nth case, you've got n minus 1 factorial up front. Okay, and the sign is alternating, so I need to put in a negative 1 to some power. So here's negative 1. And let's see, when the derivative is even, that's when the negative shows up, right? It's negative for the second derivative, but it's positive for the third derivative, and then it's negative again. So it should be negative 1 to the n plus 1. Okay, that'll be fine. So that'll make the, whether or not it's positive or negative will be the opposite of whether or not it's even or odd. And what else? So we just have the last part, right? So it's going to be 1 plus x. And then what's going on with all these other cases? Here there's a 4 here, and it matches the 4 there, and so on. So this must be minus n. Okay. So now we found the nth derivative. So let's, do a reality check or whatever and wake up and kind of figure out what it is we're trying to do. We want to figure out Cn, which is the nth coefficient of the power series expansion. So what we really care about is what happens when you plug 0 into the nth derivative. So what happens when we plug 0 into this thing? Let's see. Well, you just replace x with 0 everywhere. That just makes this 1, and so you can kind of forget about that part. And it just becomes n minus 1 factorial times that negative 1 thing. So n minus 1 factorial times minus 1 to the n plus 1. And now we're really close to being able to write down the formula for Cn. So what do you have to do? You have to divide this thing by n factorial, right? So okay, so let's do Cn is going to be equal to this stuff. So n minus 1 factorial times negative 1 to the n plus 1. And on the bottom we're going to have n factorial. Okay, alright. So you probably remember that n factorial, another way to think of this is n times n minus 1 factorial. Okay, so there's something in common. There are lots of things in common between n minus 1 factorial and n factorial. So you can cancel this and that, you know what I mean? So this simplifies to minus 1 to the n plus 1 over n. Okay, and I can draw a better n than that. And that is the formula for Cn. So great. Now we can write down the Taylor series the Maclaurin series, which is just the Taylor series centered at 0, for the function natural log of x plus 1. It's equal to, so what do we have to do? It's already written down for us right here. It's just that we have to fill in what Cn is. So it's this Cn that we just found, which is minus 1 to the n plus 1 over n times x to the n. And we go from n equals 0 to infinity. All right. Actually, this rule, notice, there's something kind of irritating going on here, right? The reason that I'm a little flustered is because if you put in 0, you get infinity on the bottom. But the rule that we found for the derivative, for the nth derivative, the 0th case is an exception, because that's the natural log case. Because the 0th derivative of the function is the function itself, so should really say this, and then plus, outside the sum, natural log of 1, okay, so why did I say that? Because the 0th derivative of the function is natural log of 1 plus x, but when you put in 0, you get natural log of 1. But look, natural log of 1 is just 0, right? It's nothing. So turns out nothing there really to get upset about. Okay, so now we have the form, all right? And let's go ahead and find the radius, or the interval of convergence. So what this means is we want to ask ourselves, for what x values does this thing actually converge? So we have an official way of doing that with the ratio test, right? If you're experienced, you don't need to go to all that trouble, because you can just look at this thing and you can see that if you put in an x with absolute value greater than 1, it's going to diverge, because you're going to have something bigger than 1 being raised to successively higher powers, and so it's going to become enormous. On the other hand, if you put in something with absolute value less than 1, you're going to be okay. Maybe we should just go ahead and do the ratio test, huh? So let's do the ratio test. Alright, so what do? We do the limit as n goes to infinity of a to the n plus 1 over a to the n. Okay, this is just for a generic series where an represents the term. So for us, an is going to be this whole big mess of things. Okay, and we can take the absolute value here, so that -1 is not something we need to worry about. And this is going to be equal to some L, and we know the interval of convergence is just going to be the values for x that make L less than 1. So this is kind of our mission. So let's set it up. Let's do the limit as n goes to infinity of, what have we got? We've got x to the n plus 1. I'm ignoring the -1 because of the absolute value signs, over n plus 1. And then dividing is the same as multiplying by the reciprocal, so I can do n over x to the n here. Okay, and this x, the x's cancel. This becomes the limit as n goes to infinity of the absolute value of x over n plus 1. All right. So the x now no longer has anything to do with n, so you can take it out of the limit. And then you have the limit as n goes to infinity of just n over n plus 1. And you can see 1,000 ways that this is equal to 1. So for example, just use L'Hopital's rule once. And you see that the answer is the absolute value of x. So this is L. Remember, we still have to find the values where L is less than 1. So to do that, you get rid of the absolute value signs by setting this up. You look between -1 and +1 and solve, and the solution here is this, from -1 to 1, the open interval. And you probably remember, I doubt this is the first time you've done this, right? The ratio test says that when L equals 1, it doesn't tell you what the conclusion is. So we have to check these endpoints plus and -1 manually. So go back up here to the series we found. What happens when you plug in +1 for x, then you get the alternating harmonic series which converges. Okay, so the 1 is actually included in the interval of convergence. What happens if you put in -1? Then you get -1 to the n times -1 to the n plus 1. It's going to be the same as let's see, -1 to the 2n plus 1. Alright, and look, now no matter what you put in for n, this is going to be an odd number, and so it's just the same as being negative. So what you get when you put in -1 is the negative harmonic series. So -1 over n. And this thing just diverges because the harmonic series diverges. So this -1 is not included. Alright, so this is the interval of convergence. And super fantastic. Number 1, our part A, is completely done. So just to review, we found the polynomial. Here's the Maclaurin series. And then we found the interval of convergence right here. It's -1 to +1. And we can even see a picture of this thing if you want. I need to adjust this. So I wrote this little program in Sage. So let's change the function to natural log of x plus 1 and redo the thing. Okay, so this is what natural log of x plus 1 looks like. It's a left shift of natural log of x. And what this is showing is, geez, how many are those? The first 23 Taylor approximations. And what it really is, you know, you can truncate the Maclaurin polynomial at a certain degree. So what this is doing is this is showing you the graph of natural log of x plus 1. That's this blue line here. And then on top of that picture, we're looking at the Maclaurin polynomial approximation truncated at the first degree. Then, in addition, the Maclaurin polynomial truncated at the second degree, and so on and so forth. So it's putting all these pictures on top of each other. And you can see that we were right about the radius, or the interval of convergence. So we said that it goes from -1, not including -1. I mean, actually, now that we think about it, natural log of x plus 1 is not even defined at -1 anyway. And we go up to 1, okay, but outside that, you can see that the polynomials are not converging onto the blue line, right? They're splitting, like they're spraying against something. And so yeah, so this is only this approximation will become perfect, but only on this interval from -1 to 1. Great. So that was a lot of work, but all right. Let's man up and go on to the next thing. Cosine 3x. All right. So we're kind of getting into the groove now, right? All we have to do is figure out the rule for the nth derivative. So the 0 with 1 is the function itself. Let's go ahead and write that. So the function itself is cosine 3x. Okay. And take the first derivative, and what is that? That's minus sine 3x, and then the chain rule spits out a 3. Now what happens when we take the second derivative? Get minus cosine 3x, and then it spits out another 3, so now I have 3 squared. Alright, and let's keep going. So now take 3 derivatives. and you get sine of 3x. But it spits out another 3 by the chain rule, and so now you have 3 cubed. Alright, and so now when we get to the fourth one, the cosine part, that cycle is over. This is starting over again at cosine 3x. But meanwhile, we've picked up 3 to the fourth power, right? Okay, so we know we know what the terms are. It's not as easy to write it down just with the big sigma notation as the other one. But I guess you could do it, right? It's going to be, we get to plug in 0, right? That's going to make things easier. So remember the formula for the coefficient here. You're really just concerned about what happens when the nth derivative is 0. Thank goodness. So what happens when you plug in 0 to these things? So plug in 0, and let's take a look. So this one becomes 1, right? This one becomes 0. This one becomes negative 1 times 3 squared is minus 9. This one becomes 0. This one becomes positive 1 times 3 to the fourth power. Okay, just like this is really negative, you could rewrite that. Maybe it's better to write this as negative 3 squared. Okay, maybe you could even write this first one. We should probably be thinking of that one as positive 3 to the 0. So you can see how these things are going to go. So only the even ones show up and the sign is alternating. So that's what the Cn is. Alright, maybe we should say it like this. What is the nth derivative at 0? It's going to be negative 1 to the, what power should we use? So when the derivative is even, it's positive, so we'll just use n. So put n here, and it's got a big 3 raised to a power, right? So 3 raised to, gosh, this is kind of irritating too. I mean, really, we could do it like this. How about I make this 2 times n, because that'll, no, shucks. So just so I can write down something quickly, I will write it like this. So this is negative 1 to the n times 3 to the n if n is even, and it's just 0 if n is odd. Right? Okay, so now we just have to think of a smart way to say that. Okay, I got it. So this is like, how is it going to go? It's going to go, the first thing is going to be 3 to the 0. Okay, and then we're going to do minus 3 squared. We're going to do plus 3 to the fourth. Then minus, and so forth. Okay, so we can write this as, how do you say this? Let's just stop psyching ourselves out. So this is n goes from 0 to infinity, and you've got 3 to the 2n, and then you're multiplying it by minus 1 to the n. Alright, plus 1. So now we've got 0, and 1, no, it should just be to the nth power. Great. So fine. So the only thing left to do is to take care of this dumb n factorial. Okay, so we got the nth derivative at 0. Now we have to take care of the n factorial part. So the final formula is all this stuff over Wow, I have to be a little careful about that too. I'm sorry, I should have thought about this harder, because here I've got 2, right? And here I'm going to have 4 factorial. This is 2 factorial. So how do I fix this up? Well, it's just going to be 2n factorial, right? Okay, 2n factorial. So now we're good, and I need to put in the x, right? X to the, so let's think about that for a second. So this is going to be times x to the first power times x to the second power. Okay, so the x is also going to be to the 2n. And we finally got it. We finally wrote it down. Thank goodness. So here's the Maclaurin series for that function about, okay, so you don't need to say it, but it's about 0. It's near 0. And we can even, it turned out to be much harder than I thought it was going to be. That's why I didn't do it beforehand. So let's look at a picture. So change the function. Maybe we also don't want to do, 23 derivatives. Maybe we'd be happy just to do 3 at first. And for the function here, let's put in cosine 3 times x. Alright, so evaluate. And this is what cosine 3x looks like, of course. And this is what cosine is here, the blue line. This is cosine, and here that counts as I don't know. And here the first 2 Taylor approximations. So I guess by 3 it means the function and the first 2. So this red line is going to be the first Taylor approximation. Notice that first means that the degree is 1, and so that's why it graphs as a line. Second means degree is 2, that's why it graphs as a parabola, and so forth. So now let's turn it up to 30 and see what's going on. And you can see, it's kind of pretty. These things, there doesn't seem to be any interval of convergence. So these things seem to be glomming onto cosine no matter how far we go out. And we could do a quick check of the formula to make sure that's really true. So I'm going to leave it to you to find the interval of convergence of this thing, but basically, what's happening here is that x is going to be some fixed number. Then the dominant parts on top are going to be 3 to the 2n power, and then this other number to the 2n power. But they're just going to get smoked by 2n factorial, and that's going to make this whole thing converge for all x. And so the interval of convergence for this one is just all real numbers. So from minus infinity to infinity. Okay, just one more to go. So the last one is x times e to the x. So the lazy way to do this would be to write down the Maclaurin series for e to the x, which hopefully you've memorized, hint, hint, and then just multiply it by x, and that would work fine. But you can also do it, it says compute it straight from the definition, so fine, let's do that. So we need to figure out what the nth derivative is again. So f of x is x times e to the x. And now f prime of x is going to be, using the product rule, e to the x plus x times e to the x. And let's just keep going here and see if we can figure out a rule. So now the second derivative is going to be, just leave this first part alone, and now it's like the head of it spawns. Can you see this like the head of a snake? So now it extends itself as another one of these. So it's another e to the x plus x times e to the x. This is almost kind of like the game of life or something. This thing is just reproducing itself. It's getting longer and longer and longer times x e to the x. Okay, alright. And we could even you can factor out these e to the x's. This is really e to the x times, how many are there? 1, 2, 3, plus x. Okay. Alright. So now it seems safe to say that the nth one, not the fourth one, but the nth one, what is it going to be? It's going to be e to the x times n plus x. And remember, what we really care about is the nth derivative with 0 plugged in. So why is that? That's because of the formula. The formula is here, right? So 0 plugged in is what we really care about. And so that just gives me e to the 0 times n plus 0 is just n. All right. So now Cn is going to be that over n factorial. So it's n over n factorial. So what is that? That's just 1 over n minus 1 factorial. Okay, so good. So what do we have to do? Let's go ahead and write it down with sigma notation. So the sigma notation expression is Cn is this, and you've got x to the n. So very simple, very easy to write down. And if you do it what I call the lazy way, you'll see that you get the same thing. Alright, then you have to deal with negative 1 factorial. What the devil does that mean? So let's just start this thing at 1. Okay, so that's fair. It's fair because I guess I'm kind of cheating a little bit because I'm doing it the other way in my head and I'm seeing that this is what it's supposed to be. Alright. Oh, here's the reason. So if you think about it, the 0th derivative is an exception, right? The 0th derivative, when you plug in 0, it doesn't, well, it turns out to be 0. And, right, so that just gets annihilated. So it's 0 anyway, so why count it? So let's just start at 1. All right, now what? Well, we've done it. And what's the interval of convergence? Just check the interval of convergence is going to be everything here too, because the factorial is so strong. It takes a lot to overcome factorial. The interval of convergence is minus infinity to positive infinity. Okay, great. And let's go ahead and take a look at the picture. So if we do, let's set this up. So we can do, I don't know, let's just set this to 3. All right, so we'll look at the first 3 lines. And change this to x times e to the x. So x times x, and do the picture. So this is what x times e to the x normally looks like. And here it is together with the first 3 Taylor approximations. So the function itself is this blue line, just like before. And these things are glomming onto it pretty fast, huh? It's because there's not anything very big in the numerator of this expression, just x to the n. And the n factorial is going to make this converge really quickly. So you could even see what happens. Let's look at the first, I don't know, 7 Taylor polynomials. So here they are. You can see them really kind of feathering onto the function. And it really, with small degree, even out to 7, becomes a very good approximation for the function in the neighborhood of 0, right? But if you go out to the 7th place, it's not going to be a very good approximation for the function at -3. If you want an approximation of the function at -3, then you need to use the Taylor series rather than the Maclaurin series, and you need to make a equal -3. Anyway, we have accomplished what we set out to do. We have found the Maclaurin series, and we have also found the interval of convergence for these 3 things, and that's all.